The last part of today's lecture is just a small note on the idea of definite matrices. And here's the idea behind definite matrices. We say that a matrix A is positive definite, and usually we require this to be symmetric and square. We say it's positive definite if, given any vector x, if I multiply it like this, where I first multiply the transpose of the vector times A and then by x, I'm going to get a number. Okay, hopefully you should see that. X is, if A is an n by n, then this is going to be a 1 by n, and this is going to be an n by 1, right? So therefore, the result is a 1 by 1, a number. If this is strictly bigger than 0, we say that the matrix is positive definite. And that needs to hold true for all vectors, okay, in Rn. On the other hand, if this quantity is less than 0, we say it's negative definite. If it's bigger than or equal to, we say it's positive semi-definite, negative semi-definite. But what we worry about mostly is positive definite, negative definite. Now, how do we show that the matrix or a matrix is positive or negative definite? Well, as it turns out, if all of the eigenvalues of a symmetric, it's important that it needs to be symmetric. If A is square and symmetric, then as it turns out, if all the eigenvalues are strictly bigger than 0, then it's true. This holds true. Okay. There's a small little proof for that. I don't remember if I can recall what that is off the top of my head. Basically, if there's a proof that says if a matrix is symmetric, then the eigenvalue matrix inverse is just equal to the transpose of the eigenvalue matrix. So what you can end up doing is rewriting this as CTX, which means if you were to group, if you were to say let y equal, let's see, oh, and I'm sorry, that's not A. What am I doing here? That's the lambda, the big lambda. If you were to say let yt equal xt and c, then y must equal ctx, right? Because remember, the transpose of this is just the transpose of this over here, and the transpose of that over here, and the transpose of the transpose is just the original matrix. So we get this quantity, which means we have two quantities to replace here. This is just yt lambda, and then this is just y, as we can see here. Now, as it turns out, if all of these here, if you were to do, work out the math of this, right? Let's suppose this is y1 to yn. Because this is a diagonal matrix of just the eigenvalues, okay, and this is technically, column, row. And you have, if you were to multiply these two, you basically just get the summation of yi and lambda I. You can figure that out for yourself, but basically, go column by column. These are all zeros here. So you do lambda 1 times y1, right? Y2 times 0, Y3 times 0 all the way down. So when you go to lambda 2, the second one, Y1 times 0 plus y2 times lambda 2. So you get basically the summation of this. And that, what you're going to end up getting there, I'm trying to think. Oh no, I got to be careful here. I'm sorry. You don't get that. You get the vector of y1 lambda 1, y2 lambda 2, yn lambda n. And if you multiply that times the other y, y1, y2, yn, right? And again, here you're going to end up getting a 1 by n. So this is actually another row. You get this times this, which is y squared times lambda 1 plus dot 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 yn squared lambda n. So the only way that you are absolutely guaranteed to have this as positive definite is if every eigenvalue here is positive, right? We just went through the math. We showed that this is equivalent to these y's here, and it doesn't matter what we assign the y's, we're always going to get a squared here when the matrix is symmetric. What this simply means is that if all of the eigenvalues are positive, then that means I'm going to get a strictly positive quantity over here. And that means that for all x, if it's true for all y, it needs to also be true for all x, which means, put differently, if all the eigenvalues are strictly bigger than 0, I have a positive definite matrix. That's extremely important for when we get to calculus 3, because remember those first and second order conditions that we needed to use in order to determine whether or not something was at a minimum or a maximum. We looked at the second derivative. As it turns out, when we look at calculus 3 and we go to optimize things there, we're still looking at second derivatives, but what we're actually going to do is look at a matrix of second derivatives where we're going to need to understand, is that matrix positive definite or negative definite? Because that's going to tell us whether or not a critical point is going to be a minimum or a maximum. So this concludes our lecture on matrices. In the next lecture, we will go through how to do matrices in Python. I can understand that a lot of this appears to be intimidating, but to be completely honest with you, a lot of this is just straight notation. So if you understand the underlying conceptual concept, then the only thing you really need to thoroughly understand is how to put all this stuff in a computer. I might ask you on an assignment just so that you can demonstrate you understand the background. I'm going to ask you to work through, some problems on this, but in practice, you're going to be, you compute these things by using the computer. Okay, the computer is what computes the eigenvalues, the eigenvectors, the inverse matrices. They do the solving, they go through the Gauss-Jordan elimination, they do all that. Computers do all of this for us these days. However, it's still important to at least have an understanding of what this stuff is. Now that you do, our next lecture will focus more on how to go about doing this stuff in software.